The LZ-129 Hindenburg was a massive achievement in 1930s engineering. At 245 meters, it was larger than any aircraft flying today, equivalent to 3 Boeing 747s placed end-to-end. Inside the massive frame, the vehicle was built for sustained luxury transatlantic operation. Passengers dined and slept in stable, climate-controlled environments, suspended by lighter-than-air lift. On May 6, 1937, the Hindenburg was destroyed. In exactly 34 seconds, the largest flying machine ever built suffered total hull loss. Despite the speed of the fire, 62 of the 97 people on board survived. That survival rate suggests that even though the fire was total, the breakdown of the ship's systems followed a specific, detectable path. Looking at the wreckage, the duralumin skeleton appears to have held its shape as it hit the ground. This suggests the physical structure itself wasn't the weak point. Instead, we have to look at the materials the frame was forced to carry. To understand how a structure of this scale failed so violently, we have to look past the standard historical narrative and deconstruct the event as a forensic engineering investigation. This schematic represents a fault tree analysis. Engineers use this to work backward from a catastrophic result, mapping the sequence of physical failures. We'll deconstruct the hull loss in 3 steps: analyzing the rapid thermal spread, isolating the ignition source, and identifying the root cause. A disaster of this scale occurs when several independent vulnerabilities align in a lethal sequence. The common explanation of a hydrogen explosion is incomplete. It misses the specific way the airship's own engineered systems combine to destroy the vehicle. Our first variable is the extreme speed of the thermal spread. Under standard atmospheric conditions, a 245-meter structure should not burn completely in 34 seconds. The speed of the fire reveals the internal gas cells were only part of the problem. The airship was a dual combustible environment, with fuel on both the inside and the outside. This cross-section shows the relationship between the internal fuel and the exterior. The outer fabric skin was coated in a chemical compound designed for aerodynamics. Those chemicals acted as an accelerant, allowing the fire to race laterally across the hull faster than the gas inside. If only the internal lifting gas had burned, the fire would have remained localized, potentially giving the crew time to execute a controlled descent. The rapid destruction was only physically possible because the vehicle's structural skin acted as a high-speed fuse for the gas inside. Moving down the fault tree, we must identify the mechanism that initiated the burn. The environmental conditions over Lakehurst, New Jersey provided the energy. A severe thunderstorm had highly charged the surrounding air, creating a massive buildup of static electricity across the airship's metal frame. The state of the vehicle changed the moment the crew executed a standard mechanical action, dropping the landing ropes to the personnel on the ground. Because those soaked ropes were no longer insulators, dropping them created a conductive electrical path, connecting the charged airship frame directly to Earth. Grounding the wet ropes forced the static charge to rapidly discharge, generating a spark. That spark required fuel. The forensic consensus identifies a localized gas leak venting into that exact space. The ignition was the result of 2 independent events perfectly overlapping: a routine environmental static discharge meeting an uncontained gas leak. This leads to the final question. Why was a passenger aircraft carrying a highly reactive, flammable lifting gas in the first place? This chart compares the properties of the 2 available lifting gases. The Hindenburg's entire safety architecture was designed for helium. While hydrogen offers more lift, helium has a flammability index of absolute 0. It cannot catch fire. The failure to use helium was a supply chain constraint. The United States controlled the global supply and enforced a strict export ban, denying German engineers access to the material. To keep the program operational without the required material, designers substituted helium with hydrogen, an abundant but highly volatile alternative. That material swap bypassed the safety mechanisms built into the vehicle. A static spark and a gas leak in a helium system is a minor maintenance issue. In a hydrogen system, it is catastrophic. The disaster was set in motion when the material specifications were changed. The safety features of the design no longer applied to the gas inside, and a safe aircraft became a hazard. Returning to our fault tree analysis, we map the complete sequence. A material constraint introduced hydrogen. A leak met an environmental grounding, creating a spark. The spark ignited the gas, and the skin accelerated it, causing total hull loss. The engineering takeaway is that the physical architecture of a system cannot be separated from the materials it was designed to contain. Materials matter exactly as much as the structural design. The Hindenburg was well built, but its safety features were calculated for inert gas. They offered no protection once that parameter shifted. When external constraints force engineers to violate a system's foundational assumptions, the original safety design ceases to exist. At that point, catastrophic failure becomes a matter of when, not if.